What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 4, Section 2, Modeling with Linear Functions. Let's do it. Explain how to find the input variable in a word problem that uses a linear function. So when we're talking about an input variable, the input variable is almost synonymous with the independent variable. Now, for a linear function, in most cases, that's going to be x. But now, if we're talking about a scenario, it's going to be the variable that is influencing another variable, aka the one dependent variable. So an example I like to always go to is if you think about the weather and the clothes you wear, right? The weather is happening. That's an independent variable, and that's influencing the dependent variable, which in this case would be the amount of clothing you'd wear, right? If it's colder, you wear more clothing. If it's warmer, you need less, etc. So that's how you identify or find an input or independent variable in a word problem. Boom, done. The initial value in a word problem is the value that you're going to get when your independent or input variable is set to 0. And that is exactly what makes it that initial value. So sometimes that independent variable might be time. It might be at time 0. When no time has elapsed, what's the starting value? That's how you do it. Boom, done. This question has to find the area of a parallelogram bounded by the y-axis, x equals 3, 1 plus 2x, and the line parallel to that at 2, 7. So what we're going to do initially is I'm going to actually graph these lines out so we can see what the parallelogram looks like. So first of all, let's graph the line x equals 3, which is a vertical line at x equals 3. Then we're going to graph this line y1 plus 2x. 1 is the y-intercept and 2 is the slope, meaning we're going up 2 over 1, up 2 over 1. Then they said there's another line that goes through 2, 7 that is parallel to the line. So here's 2, here's 7. So we're going to do another line with a slope of 2 coming down. And then the last piece is the y-axis, which is going straight up and down here. So now we're going to fill in what the actual parallelogram is. Okay, so I kind of outlined that parallelogram in red. And now we can get to the business of calculating the area of this parallelogram. The way that we can calculate area most easily is in the formula area equals base times height. So what is base and what is height? Base is simply put whichever, it's one of the sides. You can choose whichever one, right? I'm going to choose this side. The reason why is because it makes it easy to find the height, because the height is that perpendicular length, right? Going straight up, which I can see is clearly 3. And then we've got a height of 2, right? 1, 2, that's that length right there. So to get the area of the parallelogram, it's 2 times a height of 3, which is 6. Boom, done. Find the area of a triangle bounded by the y-axis, the line 9 minus 6, 7x, and the line that is perpendicular to f of x, right? That one that passes through the origin. Okay, so once again, we have the y-axis straight up and down like that. Now let's plot this line. We have a y-intercept of 9 and a slope of negative 6/7, meaning we're going down by 6 and then to the right by 7, right? When we have a negative slope, you got one of the values has to be negative, the other one has to be positive. So we said down 6 and then to the right by 7. And then when we have a slope that's perpendicular to this, it means the slope is the opposite reciprocal. So this is a slope of negative 6/7. The other line would be a slope of positive 7 over 6. And it stems from the origin, right? So we can start with the point at the origin and then go up 7 to the right by 6, like so. So here I outlined the triangle in green, and that's what we have to find the area of. So to get the area of a triangle, it is 1/2 base times height. So I'm going to assign the base in this case as this length here, and then the height is going to be that height going straight up to that vertex. So the real question is I need to figure out what is that vertex, aka where does this line intersect this second line? I can actually write a function for my second line because I could say g of x equals a slope of 7, 6x with the y-intercept of 0, right? Because it goes through the origin. So there's our equation. Now, if we set these two together to equal to each other, we can solve for x and figure out exactly what that height is. So first, I'm going to add 6/7 x to both sides like so. Now here, we're going to get a common denominator of 42. That becomes 49 over 42x. This becomes, let's see, 36 over 42x. And if we're going to add these two together, 49 plus 36, that's 85 over 42x. And this all, of course, equals 9. Last but not least, let's multiply this side by the reciprocal of 85 over 42, and we get x equals 378 over 85. And that's literally this point of intersection right here. That is the height. So now going back to 1/2 base times height, that base goes from 0 to 9, so it's 1/2 9 times 378 over 85. And as we plug it into the calculator here, we get 20.01. We'll round it there. So the answer is 20.1 square units. Boom, done. The town's population has been decreasing at a constant rate. In 2010, the population was 5,900. By 2012, the population had dropped to 4,700. Now it says predict the population in 2016. So first things first, we need to calculate our slope, aka rate of change. So I'm going to write these out as coordinates. I'm going to stack them on top of each other and then do my slope calculation. So we're going to subtract down 5,900 minus 4,700. We do the difference of the y's, the rise, over the run, the difference of the x's in that same order, subtracting down 2012. And what do we get? We get positive 1,200 on top and negative 2 on the bottom. And this comes out to negative 600. So that's a slope of negative 600, meaning the population is decreasing by 600 every year. So if we want to go through to 2016, we can kind of guesstimate like, okay, it's going to drop 600, 600, 600, right? The number of years since 2012. Or we can create the equation and plug and chug. So I'm going to opt for the equation and I'm going to plug in, and then I'll show you how the other method would work as well. So using point slope, we can say y minus, let's take this coordinate, the top one, y minus that y value 5,900 equals negative 600, the slope, times x minus the corresponding x value, which is 2010. Now as I distribute, I get y minus 5,900 equals negative 600x, and we get positive 1,206,000. And then we're going to add 5,900 to both sides like so. We get y equals negative 600x plus 1,200,000, and that becomes 6,000 plus 5,000 is 11,900. So there's a nice equation that models the situation. So now I can plug in any year I want and get my answer. So here I can plug in 2016 and I should get my population. So when I multiply 2016 to negative 600, I get negative, we're running out of room here, negative 1,209,600 plus 1,211,900. Last but not least, let's combine these guys together. And I get a final answer of 2,300. So this is the population in 2016. So now I can show you how to arrive at this answer using the other method where we just sort of count down by 600 every year. So check this out. In 2013, let me write it down. 2013, it would be at 4,100. In 2014, drop again by 600, it'd be at 3,500. In 2015, it would be at 2,900, right? Dropping 600 again. And then 2016, once again, it would be at 2,300. So there we go, double verified, boom, done. For the following exercise, consider the scenario. A town's population has been increased at a constant rate. In 2010, the population was 46,020. By 2012, the population had increased to 52,070. Assume it continues. Predict the population in 2016. So first what I'm going to do is I'm going to represent these values as coordinates just to make it easier so the numbers are a little bit more manageable. I'm going to use 0 as 2010. That's my time 0. That's arbitrary. We just have to remember that 2010 is 0. That means 2020 would be 10, etc. And then I got 0, 46,020. And then here, I would have 2 years later, so then my input could be changed to 2. Again, you can use 2010 and 2012. It's just these numbers are going to be a little bit more manageable. Now that I have this, I can calculate the rate of change, i.e. the slope, by subtracting down difference of the y values on top over the difference of the x values on the bottom. And as I write out the x values, notice I'm going in that same order, top to bottom, just like I did for the y values, the numerator. So on top, we get negative 6,050. On the bottom, we get negative 2, and then you divide that out and it simplifies to 3,025. So there's the rate of change. It's positive. It means that the population is increasing by 3,025 every year. Now, since I've arbitrarily assigned the 0 value to 46,020 to 2010, I can use that as my y-intercept. So check this out. I already got my nice equation for this line. Y equals the slope, 3,025, x plus that y-intercept of 46,020. Last but not least, to calculate the population in 2016. If 2010 is 0, 2012 is 2, 2016 would be an input value of 6. So now all I have to do is plug and chug. Plug this in for x and I'll get my answer. So 6 times 3,025 is 18,150 plus 46,020. We add these together and we get, we get 64,170 for the population in 2016. Boom, done. The town has an initial population of 75,000 and grows at a constant rate of 2,500 per year for 5 years. Find the linear function that models the town's population as a function of t, where t is the number of years since the model began. So the way I'm going to start this is the population is a function of t, meaning p of t. And here's the deal. It gives us all these valuable constants that we're going to need. What's this, a rate? That's my slope. So the slope is going to be 2,500 times that variable t. And then my initial value, that's my y-intercept. That's 75,000. I'm going to put out here, plus 75,000. And that's it. That's how you do a linear function. There's your final answer. Boom, done. If the function p is graphed, find and interpret the x and y-intercept. So I'm going to bring up that function again of p, which is described up here, which is p of t equals my slope, which is 2,500 times the variable t, plus my initial value, my y-intercept of 75,000. So if we're trying to find the y-intercept first, that's readily apparent here. That's the initial value. So the y-intercept is 0, 75,000. And we're talking about the x-intercept. By the way, this is in terms of p and t. So really they mean the t-intercept. They mean what is the value of t when the function value p is 0. So I'm going to plug in 0 for that and we're going to solve. So then we're going to subtract 75,000 from both sides and we get 2,500 t. And then we're going to divide both sides by 2,500 like so. Boom, boom. And I get t equals negative 30. So if we were to write that in coordinate form, it would be negative 30, 0. Okay, let's interpret both of these. And by the way, both of these might not necessarily be valid, so we're going to talk about them. So for the y-intercept, that's our initial value as per usual, right? Oops, that's supposed to be 75,000. So y-intercept means at time 0, this town has a population of 75,000, okay? And time 0 is, it doesn't say what year that is, but it says at some time, and then the clock begins, and it's the linear model is valid for the next 5 years. Now, the x-intercept, negative 30, 0, if we actually think what that means, that means the time at which the population of this town is 0, because that is the y value, that is the function value. Well, this says it's negative 30, meaning 30 years prior to the current date. Now, was the population actually ever 0? I don't know, because really this model, it seems to be is meant for this year and then the next 5 years. So we don't always know if we can interpret a linear model outside of the bounds where it is described. But we could say theoretically that the population was incepted or began with the town began with the population of 0 30 years ago, theoretically. So there you go, boom, done. So again, for this question, I'm going to first pull up my linear function for this scenario, which is p of t equals my rate of change, 2,500 times t, plus my y-intercept, my initial value of 75,000. And then it's asking, when will the population reach 100,000, meaning for what value of t? And 100,000 is the function value. So we're going to plug it here and we're going to solve. So first I'm going to subtract 75,000 from both sides. And I get 2,500 t equals 25,000. Then last but not least, I'm going to divide both sides by 2,500. And we get t equals 10. So what does this mean? This means that the population will reach 100,000 in 10 years. Boom, done. So it says find the linear function that models the baby's weight as a function of the age t. So we'll say w of t equals, what's the slope? The slope is 1/2. So I'm going to write that in decimal form only because this is in decimal form. It's arbitrary. 0.5 times the input variable, right? Slope times that t variable plus the initial value, I should say, the y-intercept, 7.5. So there is our linear function. Boom, done. If the function w is graphed, find and interpret the x and y-intercept. So first I'm going to pull back the function from the previous question, which is w of t equals, and again, they give us the rate of change, 1/2 pound per month. and that nice y-intercept of 7.5. Now, this original equation or function we had created was with w and t. So when they say x and y intercepts, in this context, we're talking about t and w intercepts, okay? Basically, the x-intercept is when y equals 0, and the y-intercept is when x equals 0, again, in this case, t. So what are these values? Well, I can see the y-intercept quite clearly, aka the w-intercept. That's when t is 0, it's 7.5. That's my initial value. So we'll talk about that in a second. What about when the weight is 0? So we can plug in 0 for the weight and solve for t. So we're going to subtract 7.5 from both sides, 0.5t. Then we're going to divide by 0.5, divide by 0.5. And we get a strange answer. We get t equals negative 15, okay? Because dividing by half is like multiplying by 2. So it's negative 15. All right. So let's talk about this. The y-intercept first is a little bit easier to understand. So this y-intercept or w-intercept says that the initial weight of the baby when being born at time 0 is 7.5 pounds. Now, this one's a little bit more interesting. If we were to apply it, and it's not necessarily applicable, but if we were to try and apply it to the baby, we'd say 15 months prior to the child being born, the baby being born, it had a weight of 0. Now, of course, we know the gestation period is really 9 months, so this doesn't really make sense. And this model, as it mentions, is meant to apply only to the first year of being born, not back in time. But if you were to interpret it, we would say 15 months prior to being born, it had a weight of 0, boom, done. When did the baby weigh? 10.4 pounds. So once again, with this scenario, the first thing I'm going to do is I'm going to recreate my equation, which is w of t equals that slope, half a pound per month, so 0.5 per month, plus my y-intercept, my initial value of 7.5. And it says, when did the baby weigh 10.4? Meaning, we're going to plug 10.4 in for the weight and then solve for t. So first I'm going to subtract both sides by 7.5, boom, boom, and then we get 0.5 t equals 10.4 minus 7.5 is 2.9. And then when you divide by 0.5, divide by 0.5, again, it's like multiplying by 2, so we get t equals 5.8. So we'd say the baby weighed 10.4 pounds at 5.8 months, boom, done. The number of people afflicted with the common cold in the winter months steadily decreased by 205 each year from 2005 until 2010. In 2005, 12,025 people were inflicted. So for this function, I'm going to designate 2005 as 0 times 0, and 2010 would be 5 years later, aka time 5. And then we're going to take these corresponding y values and we're going to plug them in. So at time 0, it's 12,025. And then we don't know at time 5 or in 2010 what that value is, but we do know that the rate of change is right there. It's given to us. So we don't actually need to calculate slope. It's negative 205. So now we can create our function. So c as a function of t equals that slope negative 205 times the variable, independent variable, in this case t, and then plus that y-intercept, that value, the initial value at time 0, which in this case is 2005, is 12,025. And there's your function. Boom, done. For 27, it says find and interpret the x and y intercepts. So once again, I'm going to bring back our function for this situation. So this is the function because it says it changes or decreases by 205 each year. That's a slope of negative 205. Negative indicates the decrease. And then the y-intercept is the initial value. And in this case, our initial year is 2005, so hence 12,025. Now, our y-intercept is simply 0, 12,025, that initial value that we were given. And again, when I say y-intercept, really in this case, I'm talking c-intercept because it's a function c, but that is the y value. And then the x-intercept, or in this case, it would be the t-intercept, is when the c value is actually 0. To calculate that, we're going to actually plug in 0 and solve for t. So now that I've plugged in 0, I'm going to subtract both sides by 12,025. And then last step, we're going to divide by negative 205. And what we get is approximately 58.7. So we can put that in here. Now let's interpret both of these values. So again, the initial value means that the amount of people that were inflicted in 2005 at time 0 in this case would be 12,025 people. And what about the x-intercept, or in this case the t-intercept? This means that it's going to take this amount of time until the number of inflicted or affected goes to 0. And the amount of time it's going to take is 58.7 years. So there's your answer. Boom, done. When will the output reach 0? So again, I'm going to pull up my linear function for this scenario with a slope of negative 205 and a y value of, or y-intercept of 12,025. Negative 205 times t plus that initial value, 12,025. When will the output reach 0? So to figure that out, we're going to plug 0 in for the c value, and we're going to solve for t. So I'm going to subtract 12,025 from both sides equals negative 205t. Then we're going to divide by negative 205, divide by negative 205, and we get t equals 58.7. So that's 58.7 years after 2005, and it says when, meaning what year. So what year is it 58.7 years after 2005? Well, 58 years, but 58 plus 2005 is 2063. It's going to happen some point in that year. So the answer is 2063. Boom, done. So here it says find the linear function y, where y depends on t, the number of years since 1980. Now, we don't have the y-intercept per se. We can't see the full graph, but I can see these really great 2 points here. And I'm going to identify them as this one looks like 15, 150, and this one looks like 25, 130. So again, when we have 2 points, we can start by calculating the slope. So let's do that. So we're going to stack the coordinates. And then what we're going to do is we're going to subtract down difference of the y's first. So 150 minus 130 on top over the difference of the x's. Again, rise over run, right? 15 minus 25. And that gives us 20 over negative 10, which simplifies down to negative 2. So there's my rate of change. There's my slope. Okay, and that makes sense. This does look like a negative slope. Now let's get our equation with, or that nice linear function, but we need to use point slope because we don't have a y-intercept. So let's just use this top point, 15, 150. So check it out. It's y minus the corresponding y value, 150, equals my slope, negative 2 times x, or in this case, we'll say t because that's a variable here, t minus that corresponding x value of 15. To get this into slope-intercept form, which is what we want, we're going to distribute, and then I get y minus 150 equals negative 2t plus 30. So last but not least, we're going to add 150 to both sides to isolate the y. So we get y equals negative 2t, 30 plus 150 is 180. There's the final answer. Boom, done. So for 33, it says find and interpret the x-intercept, but in this case, that's actually not shown on the graph. So if you want to see how we got the linear function for this scenario, go back to 31. I'm not going to go through the whole process again for 33, but I'm going to write it up and we're going to use it going forward for this problem. So here's the function, and we want to know what is the x-intercept. This is the point when y equals 0. So we're going to plug in 0 and we're going to solve for t. So right, they said x-intercept. They mean the independent variable. They mean t. So we're going to keep going and isolate. We're going to subtract both sides by 180. And then we're going to divide by negative 2. T equals 90. So that means it will take 90 years from 1980 to hit a profit of $0,000, aka in 2070, right? That's 90 years from 1980. In 2070, profit will be 0. There's your answer. Boom, done. Figure 8, which shows the profit of y in thousands of dollars of company in a given year, where t represents the number of years since 1980. 35 says find the linear function y, where y depends on t, the number of years since 1980. So we don't have a slope necessarily. I mean, we can calculate it, and we can't see the y-intercept because we kind of have this segment that's presented to us of this linear function. But what we do have, which is great, is 2 coordinates. We can see that when t is 15, the y value is 150. When t is 25, the y value or function value is 450. And using these points, we can come up with our equation. So the first thing I'm going to do is I'm going to stack these coordinates right on top of each other. So what we're going to do is we're going to subtract 450 minus 150 over 25 minus 15. Okay, top down, top down. 450 minus 150 is 300. 25 minus 15 is 10, and that simplifies to a slope of 30. Now let's use point slope. And we're going to arbitrarily use this point. We could have used either, but let's use this one. And now we say y minus that corresponding y value of 150 equals the slope, 30, times t, which is the specified variable here. Usually it's x. T minus that corresponding x value of 15. Now we're going to distribute. We get y minus 150 equals 30t, and then 30 times negative 15 is negative 450. Last but not least, we're going to add 150 to both sides, and we're going to put the final answer here. Y equals 30t, negative 450 plus 150 is negative 300 for the win. Boom, done. So for this question, it says find and interpret the x-intercept. And in this case, really what they mean is the t-intercept. So what I'm going to do is I'm going to pull up the linear function for this scenario, which we actually did in 35. So I'm not going to redo that entire process, but if you want to see how we derive that linear function formula, go back to 35. So the x-intercept is the value of t, or x, in a normal y-x situation when the y value, the function value, is set to 0. So we're going to set that to 0 and we're going to solve for t. So I'm going to add 300 to both sides equals 30t, and then I'm going to divide by 30, and we get t equals 10. And so there is my x-intercept or t-intercept. It's 10. So again, 10 means the number of years since 1980. So that means 10 years after that would be 1990. So it's saying in 1990, the profits, right, because this represents profits, the profits for this company were 0. So apparently it started growing in 1990 and got bigger and bigger. And we only see here 15 years later, which is in 1995, the profits seem to be at 150,000. So there's your answer. Boom, done. For the following exercises, use the median home values in Mississippi and Hawaii adjusted for inflation shown in table 2. Assume that the house values are changing linearly. So we're assuming, or we're given that as an acceptable assumption. It says, in which state have home values increased at a higher rate? So what are we talking about, higher rate? We're talking about rate of change, aka slope. And we have values for both of these that where we can calculate that rate of change per year. So again, slope is the difference in the y values, in this case, the difference in the cost over the difference in the x values, in this case, the difference in time. So for both of these, 50 years has elapsed. So what I'm going to do is I'm going to kind of say, for the rate of change for each of these, we're going to be dividing by 50, right? 2000 minus 1950. And then here, we're going to also subtract. In this case, I guess we're going up just to keep it positive, right? But we're doing 2000 minus 1950, 50 on the bottom. And then for Mississippi, we're going to do 71,400, right? Minus 25,200. And then for Hawaii, it's going to be that bottom value, 272,700 minus 74,400. So when we simplify this value for Mississippi, it's a rate of change or a slope of 924, meaning it's increasing by $924 per year. And then for Hawaii, it simplifies to 3,966. That's a rate of change. That's a slope. That's the increase per year. So the one that has the larger increasing at a higher rate would be Hawaii. So Hawaii is the winner. Boom, done. If we assume the linear trend existed before 1950 and continues after 2000, the two states' median house values will be or were equal in what year? So what we're going to do is we're going to create these equations for both of these states based on information that we determined in a previous question. So first, I'm going to get the slope. And again, remember, 1950 is going to be my year 0. 2000 is going to be my year 50, right? 50 years from 0. And to calculate the slope, I take the difference of these two values. I'm going to subtract actually up in this case, because I'm going to get a nice positive value. And then I'm going to divide that value by 50. I'm not going to write it all out because I did it in a previous question in 39, but I'm going to go ahead and do that calculation now. And we end up with a slope of 924, a rate of change. That's how the median price is changing. And then we're going to do the same for Hawaii. We're going to subtract 272,700 minus 74,400 divided by 50. And we get a slope of 3,966. And then since we're trying to figure out when these two are equal, we want our equations for both of these median price homes to be set equal to each other. All we need now is the y-intercept for each. Again, that's at time 0, which we've designated as 25,200 or 1950, but 25,200 here. Set that equal to Hawaii, which would be plus 74,400. Now we got an equation that we can just simply solve for x. So I'm going to simultaneously subtract both sides by 25,200 and also subtract both sides by 3966x, like so. So when we subtract these, we get negative 3,042x equals 49,200. Okay, now we're going to divide by negative 3,042 and we get approximately negative 16.27, okay? So what does this mean? We want to figure out negative 16.27. How do we apply that to the year? Well, that is 16 years, a little bit more than 16 years prior to 1950. So basically it's like 1950 minus 16 years, which would be 1934. But then it's a little bit more, right? That extra 0.27. So that would set us somewhere in the year 1933. Boom, done. For 43, it says, what would be the median home value in Indiana in 2010? So again, I want to come up with that nice linear equation for Indiana in particular, and then plug in 2010. So we're going to start by saying 1950 is going to be year 0, 2000 is going to be 50 years from that. So kind of like an x value of 50. And I can use this to calculate our rate of change, aka the slope for how the median house prices are changing. So I'm going to subtract 94,300 minus 37,700 divided by 50 minus 0, which is 50. And this gives me a slope of 1132. So that's 1132. And then now to get my nice equation to predict median value, it's that slope times x plus my y-intercept, which I've designated as 37,700. That's times 0 in 1950. And now to get 2010, what represents 2010? 50 represents 2000. Therefore, 60 years from 1950 would be 2010. So I'm going to plug and chug. I'm going to plug in 60 for x and evaluate this, right? 60 times 1132 plus 37,700, which evaluates to a median home price of 105,620 for the win. Boom, done. In 2004, school population was 1,001. By 2008, the population had grown to 1,697. Assume it's changing linearly. How much did the population grow between 2004 and 2008? So this is just a straight subtraction problem, right? It went from 1001 to 1697. That's a net change of 696. How long did it take the population to grow from 1001 to 1697? Well, that first value was in 2004. The second value was 2008. Therefore, that is 4 years. What is the average population growth per year? I love that word per because it automatically tells you need to be dividing. It's the amount of growth divided by the amount of years. So it's 696 divided by 4, which comes out to 174 for part C. Now to answer D, what was the population in the year 2000? Let's create a nice equation first, which would be the population Y is equal to that rate of change, it's growing, or positive 174x, plus what's our times 0? 1,001. And what we have to recognize is times 0 is 2004. So if we're trying to find 2000, okay, that's 4 years prior to 2004, meaning I'd have to plug in -4 for x. And when we evaluate that, we get 305. So 305 is the answer for part D. Now it says find an equation for the population of P t years after 2000. So now 2000 is actually my times 0, okay? So that's my, whatever the population was in 2000, that's my y-intercept, which I already know is 305. So my equation would be P as a function of t equals my slope 174 times t. Now we're not going to use x because they said, hey, let's do it in t, plus that y-intercept of 305. And last but not least, we're trying to use the equation to predict the population in 2011. Well, since time 0 now is 2000, 2011 is 11 years after, meaning the value of t we plug in is 11. So let's plug that in and evaluate. So there we have 174 times 11 plus 305, which gives a final answer for part F of 2,219 people. Boom. A phone company has a monthly cellular plan where a customer pays a flat monthly fee, then a certain amount of money per minute used for voice or video calling. If a customer uses 410 minutes, the monthly cost will be $71.50. If they use 720 minutes, it will be $118. Find a linear equation for the monthly cost of a cell plan as a function of x. So if we're trying to do that, guess what? We've got some nice values here. We got 2 coordinates. So I'm going to start by mapping out these coordinates. So again, here's the x value, which is the minutes. Here's the y value, which is the cost. So now we can use this to calculate the slope, right? So I'm going to subtract down, and I got 7150 minus 118 over 410 minus 720. And we get a slope of 0.15, okay? And the last thing we need to do is we need to know the y-intercept. Well, they don't give us the y-intercept, meaning, you know, what's the cost if you have 0 minutes. So we're going to use point slope and get there on our own. So again, we're going to start with y minus, I'm going to choose the top coordinate, it's arbitrary, y minus that y value of 7150 for point slope equals my slope times x minus that corresponding x value of 410. And now we can distribute, and we get 0.15x minus 6150. Last but not least, let's add 7150. Add 7150 to both sides, and we get y equals 0.15x plus, and those two add up to 10. There's your equation for part A. Now let's talk about the slope and the y-intercept. The slope is, of course, multiplying the 0.15. So slope is 0.15. And if we're interpreting it, it's saying that's 15 cents is what's being charged per minute because it's per the x inputs, right, per minute. So 15 cents or $0.15 per minute. That's my slope for part B. And the y-intercept of 10 means that if you use no minutes, right, your baseline cost, your initial cost per month is $10 per month if you have 0 minutes. Last but not least, for part C, we're going to use this equation to calculate the cost for 687 minutes. So we're going to plug and chug. So 687 is the amount of minutes. So I plug it in for X. 0.15 times 687 is 103.05 plus 10 is 113.05. So it would be $113.05. Boom, done. In 1991, the moose population in a park was measured to be 4,360. And by 1999, the population was measured to be 5,880. Assume the population continues to change linearly. Find a formula for the moose population P since 1990, meaning 1990 is your time 0. So let's look at this. If this is 1991, that would be 1 year after. So I'm going to make a coordinate of 1, 4,360. And for 1999, that's 9 years later. And that's a population of 5,880. So if we're trying to find a formula, first I'm going to subtract down, calculate the slope. So we got the difference of the y values, like so, over the difference of the x values, like so. So when we subtract these, we get negative 1520 divided by negative 8, which simplifies to a slope of 190. So it's increasing by 190 per year. Now we can use point slope and come up with the equation for 1990. So check this out. I say y minus, I'm going to use the top coordinate arbitrarily, which is 4360 equals my slope 190 times, just making a little bit more room, x minus the corresponding x value, which is 1, like so. And now to get this final equation in slope-intercept form, we're going to distribute, and we got y minus 4360 equals 190x minus 190, and then we're going to add 4360, So once we add this together, we're going to get, and instead of y, now I'm going to change it to p of t, right? It's a function of t. I get p of t equals 190t, and then 4,360 plus negative 190 is 4,170. So there's my answer for part A. For part B, it says, what does the model predict for 2003? So since 1990, that's 13 years from that point. So I'm going to plug 13 in for t for part B. So we'd have 190 times 13 plus 4170. And when we plug it in, we get 6,640 for the win. Boom, done. The Federal Helium Reserve held about 16 billion cubic feet of helium in 2010, is being depleted by about 2.1 billion cubic feet each year. Give a linear equation for the remaining federal helium reserves, R in terms of T, for the number of years since 2010. So 2010 is going to be our time 0. So we can create our two coordinates here, 0, 16. Again, it's in billions, right? Let me see. Does it say in billions? It doesn't say in billions, but let's do it in billions so we don't have these crazy big numbers. And then it says the rate of change is 2.1. And since it's being depleted by that, it would be negative 2.1, which means now we have enough information for a nice equation. We can say that it is R of t equals my slope, negative 2.1 times t, plus my y-intercept of 16, and there's A. For part B, we're plugging in 2015. So how many years is that since time 0? That's 5 years. So I'm going to plug in 5 for t, and we're going to evaluate this. Once we evaluate this, it becomes 5.5, so it'd be 5.5 billion cubic feet for part B. And last but not least, for part C, in what year will it be depleted? AKA, when is it going to be 0? So we're going to set this whole thing equal to 0, and then we're going to solve for t. So I'm going to add subtract 16 from both sides. So we get negative 16 equals negative 2.1 t. Then we're going to divide by negative 2.1, and t equals approximately 7.6. So that's 7.6 years from 2010. So we can say in the year 2017, boom, done. You're choosing between two different prepaid cell phone plans. The first plan charges 26 cents per minute. The second one charges $19.95 plus 11 cents per minute. How many minutes would you have to use in a month in order for the second plan to be preferable? So let's first see. So obviously the second one eventually is going to be cheaper as you use enough minutes. So let's first see when they're equal to each other, and then we know we have to go beyond that threshold. So what is the first plan? It's 26 cents per minute. What is the second plan? It's 19.95 plus 11 cents per minute. And we're trying to figure out when these two are equal. So now we have a nice equation. Now we can solve for x. So I'm going to subtract 0.11x from both sides. I get 0.15x equals 19.95. And then when we divide both sides by 0.15, we get x equals 133 minutes. So at 133 minutes, they're exactly the same, which means that if you use more than 133 minutes, then the second option with the 19.95 plus 11 cents is going to be preferable. So more than 133 minutes, boom, done. When hired at a new job selling jewelry, you are given two pay options. Option A, base salary of 17 G's plus a commission of 12%. Option B, base salary of $20,000 with a commission of 5%. How much jewelry would you need to sell for option A to produce a larger income? So again, we're going to set these equal to each other, figure out that point of equality, and then we know that more than that, selling more than that will be better for A, because A has got the bigger percentage anyway. So obviously, eventually selling more is going to be better with A. So you're getting a base of 17,000 plus 12% or 0.12 of the sales. And then for this one, it's 20,000 plus 5% of sales. And we want to see when these two are going to equal each other. So we're going to isolate x and solve for that. So we're going to subtract 0.05x from both sides. And simultaneously, we're going to subtract 17,000 from both sides, like so. So that's going to cancel. That's going to cancel. This gives me 0.07x equals 3,000. And then we're going to divide both sides by 0.07 And that gives me approximately 42,857.14. So that's the dollar value of sales that you'd need for them to be equal. So for A to be better, we need more to sell more than 42,857.14 cents worth of jewelry. So there's your answer. Boom, done. When hired at a new job selling electronics, you're given two pay options. Option A, base salary of $20,000 with a commission of 12%. Base salary of $26,000 with a commission of 3%. How much electronics would you need to sell for option A to produce a larger income? So we're going to take both of these pay rates and set them equal to each other, figure out when they're equal, and then we need to go more than that for A to be bigger. So A is 20,000 plus 12% of sales. X is the sales. For option B, it's 26,000 plus 3% of sales. Again, that's X. We want to know when they're equal to each other. Now we're going to isolate by subtracting 0.03x on both sides and also subtracting 20,000 from both sides as well. Boom. And then we get 0.09x equals 26,000 minus 20,000 is 6,000. And then we're going to divide both sides by 0.09 like so. And we end up getting 66,666.67 cents. So for A to be better, right, to produce a larger income, you need to sell more than this amount. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.